Okay, so good morning, everybody. So as usual, I'll start with sharing the screen and walk you through our web page. All right. So we are here. So important announcement is next week is the Easter Monday, so there will be no lecture. Okay, so we will meet again in 2 weeks. So today we are here, so we will be finishing this decision making under uncertainty 2 or Markov decision processes 2. So as usual, I assume that you watched this lecture here by Dan Klein from UC Berkeley, and there's quite an overlap again with with what we are doing. So and it's really well done, the lecture. It starts with the recap of value iteration, and then it goes over to policy iteration, and you have all these explained all the details, the relationships to expecting max and all these different things. There's value iteration, there's policy iteration, there's policy extraction, there's policy evaluation. So we will just walk through quickly and make some interactive exercises. Questions to this lecture from your side? Was anything unclear? No, okay. And for the lecture after the holidays, it will work exactly the same way. We will start a new topic, which is reinforcement learning. And again, please watch this lecture online prior to our meeting here. So reinforcement learning 1. Okay. So here is an overview of the lectures from UC Berkeley. And in case you're missing some background, for example, probability or Markov models, feel free to also watch some extra lectures to if you're missing some basics. But otherwise, we will do reinforcement learning 1 and 2, and then we will see. There's also the midterm exam coming up after this reinforcement learning lecture 2. It looks like it will take place online, but I think it doesn't make sense to predict too much into the future, because we will basically have to adapt to the current situation. Okay, so that's so much for this. I can then come back to the slides, and we are here. So let me stop also the camera, that you have a bigger view of the slides like this. All right. Right. So value iteration was the algorithm that we finished with last time, and today we will, among other things, look at the alternative main algorithm for solving this Markov decision process, which is policy iteration. Recap, this is this block world that we were dealing with. Usually we started here. These were the terminal states. This is to mark the uncertainty on the outcome of the agent action. So this is the key new feature here compared to search, that you have this uncertainty. You command your agent to do something, but it may end up doing something else, and that's what complicates the problem. I think we don't need to really go into the details here. The goal is to maximize the sum of discounted future rewards. So we're dealing with sequences, a sequence of decisions and sequence of rewards, and we want to maximize that sum of those rewards. The notation: you have states, you have actions, you have transitions, which are actually conditional probabilities. I'm in a state, I do an action, and I end up in a state as prime. And for those transitions, I'm getting these intermediate rewards as I go, which may be also discounted. And this is the relation to the tree or to the expecting max. This would be a sort of max node. You're choosing the action, and this would correspond to the chance node, where there is the uncertain outcome of the action. And the important MDP quantities are policy, which is a mapping of states to actions. utility, which is a sum of discounted rewards for an episode. So the agent does a number of steps, getting these rewards as it goes, and the sum is the utility for this episode. And the value is the expected future utility from a state. So it's associated with a state. And usually we talk about the optimal value from that state, or a value following a particular policy, either the optimal policy or some policy. And we can then evaluate what will be the expected future utility given that policy. And Q values is this kind of special thing that same like values, but the action you take immediately now is given. That's the action A, and we will see, that is a convenient thing that that allows you to simplify things. In particular, it allows you to know which action to take in which state, which is something that the value doesn't directly tell you. So more of this notation. So this is the notation that is the expected value, which means it's taking the probabilities, the transition probabilities into account. And the best policy, which is denoted with this pi star, maximizes this expected value, or this expected utility. Right, so I think this is all clear. Yeah, value of a state versus value of a Q state. I think we covered that. And so in the tree, the difference is that with the Q value, this A is fixed. That means these other branches are not considered. Whereas if it's just the value, then you have to consider them all and you have to max over them. So you're sort of in that max node. And which you see here. Okay, so that's the difference. Okay. So yeah, so this will be the first interactive exercise. So you have a very, very simple maze. These are terminal states. This gives you a +10. This gives you a -10. And these are non-terminal states. And the living penalty is -1. That means for every move you make, you get a -1. The gamma is 1, so there is no discounting. And the robot is deterministic. Okay, so this is a very simple situation, but just that you see really quickly how the value iteration works. So the robot is deterministic. It can do these actions. So if it goes left, it will go left. That's simple. This up and down just means it will stay where it is. So you go up and you stay here. And yeah, that's so much for the description of the environment. And the task for you would be now to just do 1 or 2 sweeps of the value iteration algorithm. Which means, so what does it mean? That means you do this kind of this update here. This is written in terms of the Q value. This is written in terms of the value. So you're maxing over this. Okay, so Q value means you're not maxing because the action is fixed. Value means there is this additional step of maxing over the actions. And so there is this probability, but that is used only when the world is stochastic, or when the outcomes of the actions are uncertain. So in this case, we don't need to sum over these things because we have a deterministic world. So the only thing, and gamma is 1. So the only thing we have to do is this, the immediate reward plus the value of, let's say, the neighbors in the state space. Okay, so so this is the inequality. This is the the Bellman equation. But for value iteration, we replace this by this assignment thing, and that's how the value iteration works. So you have an arrow, like an assignment, instead of the equality. Okay, so task for you is here. So assume that you do 1 sweep of the value iteration algorithm, and the question for you is, what will be the values of these non-terminal states after that 1 sweep? Okay, so you can start working on that. There is A, B, C, D. So I will start a poll. So one of these three options, what will be the values after one sweep? So this one sweep means you do that update. The values from the initial values are here, what you see written here. And now you do that one sweep, which, you know, from the formula on the previous slide, basically means just summing the reward plus the initial values and that you see, you know, where you're getting with each of those actions, and taking the max. So so the value is the one that corresponds to the best action you can take. So I'll give you a little bit of time, and if you have questions, then please write it to the chat or just speak. I hope the microphone is now working for everybody who wants to use it. Okay, so I have some answers there. Grigoris, do you need more time, or is it clear how to do this? Okay, so those of you who answered got it right. Yeah, so it's fairly simple. So how do we do this? So in this case, it's really easy because the robot is deterministic, right? So we can basically, let's have a look how we would do the Q values. Okay, sorry for my drawing. But so assume the action we go left, right? So we get a -10, which is the -10 is going to be the value of the neighbor. You know, that's so rather than going recursively into the values, we just use the value that is there, which is the initial value, and plus the living penalty, which was -1. So that gives us -10 and -1. So that would be -11 for going there. I know for all the other actions, it's going to be, so it means I'm go up and I'm going to end up here. So there is no, and my value, you know, my sort of previous value, but you know, so my initial value is 0, and there is the living penalty that I will have to suffer. So it's going to be -1 all over here. And then I choose a max out of those, which, you know, can be any of them, but in any case, it's going to be -1. So this is the value here. Here, it's going to be basically, I'm not going to reach any terminal state in that one sweep. So it's going to be -1 all over the place because my neighbors have 0 and I have 0. So the value is going to be, you know, 0, and -1 is the living penalty. And here it's going to be the same. And then there's going to be a 9 here because it's the 10 and plus the living penalty, which is -1. So it's going to be a 9, and I take the maximum. So it's this one, right? Okay, so A is correct. Okay, so that's very easy. And it's very easy because it was a deterministic robot. Otherwise, if we had to consider the uncertain outcomes of the actions, we would have to sum and do this weighted average over the probabilities. Okay, so second sweep. So so imagine that you do one more sweep, and so maybe for your convenience, let's write down what were the values that we had from sweep 1. So let's say first sweep were -1, -1, 9. Okay, and so now you do the second sweep, and you get new values. So new pole. A, B, C, D. Okay. Okay, so someone thinks it's a B and it's a C, so the difference here is in this -1 or -2. So how is this going to work? So okay, so let's start maybe from what is a common. So this is going to be a 9, and that is that is clear, because you basically get only one penalty, because you start from here, you go right, it's deterministic, you get one penalty of -1, and then you get the value of 10, and that's it, because you're in the terminal state. And here it's going to be this 8, because as you go, you're going to get 2 of the living penalties, so you get this becomes, let's say, more discounted, the reward. So you see here that before we had a -1 because we didn't manage to get to the terminal state, but this is exactly how this algorithm works, that you get these rewards propagated, but you need more steps to reach them. So suddenly out of a -1 you get so this remains an 8, and I get a -1, suddenly you get an 8 here. And so how does it work here? Is it a -1 or a -2? So you don't have time in those 2 steps to get to the final reward. So so basically here you had a 9, and this this is the value of your neighbor, so this gets propagated here, so you get this -1 plus 9, which gives you 8. But here you had a -1 because from here it didn't have time to see the positive reward yet. So here you basically have a you have a -1. Okay, let's do the Q values such that it's clear. Okay, so so this is a -1. Okay, this is also, so I have a -1. If I go up, I'm going to end up here. So I'm going to have the -1, which was my previous value, and the living penalty, which is also -1. So it gives me -2. If I go here, this remains -10, and living penalty, it's -11. Here it's symmetrical, it's -2. And here, this is -1 and living penalty -2. So together it's -2, right? So it's not -1, it's -2, because this is not 0 anymore. This is -1 because it reflects the fact that I already suffered one penalty in the previous step, and then I get another one for for this extra step. So it's going to be -2. Max of this is -2, and this is correct. Okay. Is it clear how this works in this simplified situation? Wonderful. Okay. So moving on. So this is yet another way, and we're asking about the Q values. So pick the option which is wrong. So I start a new poll and then I continue talking for a little bit. Yeah, I saw that Rufat just joined. Rufat, there was a technical issue, so basically we had to leave the original conference room and we ended up opening a new one and sending the invitation to the email, and now it seems that everything works fine. So yeah, sorry for that technical issue. Right. So this means that in state 1, which is this one, if I go up, we're talking about the second sweep, so the one that we just did before, right? And so one of the options is wrong. You know, it's basically the same thing. Yeah. Okay. That's fine. So everything seems to be -2, but one of them is wrong. So it's important that these are the Q values, not the values. That means you're fixing the action. Okay. So let's write down which what are we talking about. So we're talking about this square. That means, you know, you're here in the second sweep and you're going up. We can also repeat what were the values from the first sweep, such that you can nicely add them. So first sweep, and we had -1, -1, 9. Now we're doing second sweep, and we're interested in this one, a Q value. So if I go up, what is the, you know, the expected sum of future rewards there after, you know, behaving optimally thereafter. So I'm fixing this action now, but from, you know, from then on, it's I will act optimally. But in this case, it's not really, you don't have to imagine that. You're not doing an expected max. You're just assigning the values basically from the neighboring states. You don't have to go into the recursion. Then we're interested in this one. So this is A. This is B. Then we're interested in this one. This is C. And then we're interested in this one. And this is D. And so which of them is not -2? Okay, so let's work. Okay, it seems that you're getting it. You're getting it right, indeed. So yeah, so here it's clear, right? So it's a -2 plus the living penalty. It's going to be -2. Same here. It's going to be the same here because this is the minus. I'm going to the left. This is the -2 of that state here plus my living penalty. But the right the wrong thing is C, because here it's a +9, right? So I get a +9 for going right. -1 gives me 8. So yeah, it's very simple. Wonderful. So moving on. So here you see a different a different situation. So it's still a deterministic robot, and here you see a comparison of the v values and q values. So the convenient property of q values is that the best action is clearly apparent. You can just see, you can just directly take the max, whereas from the values it's more tricky, and you need to do this what is called policy extraction from the values, which will be this one ply of expected max. And we will see this over and over, that basically all the methods discussing today, they usually do one ply of expected max. So that's kind of the point of all these that all comes from the Bellman updates, that you don't compute deep into the tree, but you just use the recursion, or you use the fact that you have already iteratively established the values of your neighbors. Right. So so this is now moving to a non-deterministic agent, still the same maze. And in this case, 80% of the time it will do what you tell it to, and 10% of the time it will go, clockwise or counterclockwise from that direction. We still have a gamma 1, and here you see the values and the q values. And yeah, I think you have also seen it in the lecture by Dan Klein, for example, looking at this square, depending on the setting. It may not be clear whether the agent should move up or left into the wall. Depends how the non-determinism is set, and also on the living penalty. And yeah, that can be extracted from the values by doing this one ply of expected max, or from the q values you just take a max. So that's very very easy. So so the value that you see here takes into account a number of things. So it takes into account the policy. So remember that the values are for the optimal policy, often can be also for any policy, but for a fixed policy, that means it has to be fixed what the agent should do in every state. The values also take into account the fact that the goal may be far away. So you see here is 1 + 1, right? That's where you want to get. Here is the 0.92, 0.87, 0.81. So this takes into account the living penalty. So you incur all those penalties until you get there. And it also incurs the non-determinism, right? Because even if I really want to go like this, I may end up, going somewhere else because of this fact. So that's what kind of discounts the numbers here even more. So the transition probabilities. And furthermore, the more steps I do, the rewards may be discounted, which is not the case for what you see here, but in general, yes. So basically, this is basically why the further you are away from a goal, the lower the numbers are. And yeah, and one final point is that it's the fact that you have, say, 0.71 here. It's not just that you're trying to get here on this, in these steps, and it only if you're lucky, in all those steps, 80% of the time you will actually get there. That's how you get to the 1. And this is so this value reflects more than that. This value also reflects that you may be unlucky as you go, but there are alternatives ways to reach the goal, right? So sometimes I go here, but I end up here. And depending what the policy here in this square, I may choose a different path, or I may choose to go and come back. And this will also add to the value, because I may eventually still get there, but I will just get more penalties as I go. So all that is reflected in the value of every square, right? So yeah, and this is the same, but with the Q values, which, which tell you basically more information. Right, so this I think we covered. So Bellman equations, they characterize the optimal values. So this is an equality. So this holds, and the value iteration algorithm turns them into an assignment where it's using the values from the previous step. So it's an iterative fixed point algorithm that will eventually get to the optimal values. I mean, we will stop before that once the difference in the update is small enough. Right. Yeah, I think we covered this, and this is explained in the Berkeley lecture, at the end of the previous one from last week. Okay, so we get to the new topic now, which is from values to policy. So remember that usually what you really need is the policy, because you need you need to know what the robot should do in every state, right? The values are a sort of intermediate thing that that is helpful, and it allows you to estimate what you can expect in terms of the future rewards. But really, what you're after most of the time is the policy. The value iteration is one way of getting you to the policy with this extra step, which is this policy extraction. But we want to learn about this other method, which works directly on the policy, and it has some advantages over the value iteration. So this is what we already talked about. If I just see the values, the optimal values, I don't see immediately the policy. I need to do policy extraction. So how do I do that? I basically do this one ply of expectimax. So that means, say I'm here, and I will consider going, in all the actions that I have, and then do the weighted sum of the values that I will get in the neighboring states. And from that, I will choose the action that has the maximum of this sum. So I do this, and then that will basically give me so I will essentially compute the Q values there, and then I choose the maximum. So it's not so much computation, because it's just one ply of the expectimax for every state, but it is some work. So note that the value iteration algorithm doesn't have to do this all the time, right? Because it just we wait until it converges, and only at the end we need if you want to extract the policy, we can. So basically, it implicitly has the policy. So at every point of running the algorithm, you could do that, and you would know what the policy right now that the algorithm recommends is. But it's not part of the value iteration algorithm. It doesn't have a sort of explicit notion of what the current policy is. Right. This is one-step expectimax. And yeah, so essentially you get the Q values, and then what is the optimal action? So that's simple. You just max over those 4 Q values. So here it's going to be 0.76. Here it's going to be 0.81. And often you can, in our simplified scenario here, you can sort of use common sense most of the time. But for some squares like this one, it's tricky, and just because you see 0.66 doesn't immediately give you the answer what is the action. So in this case, it is the action up, but you can just tweak a little bit for example, the penalties or the determinism of the agent, and this will suddenly become the best action to take here. So here you actually have to do the math by doing this, this one ply of expectimax, considering the outcomes of the 4 actions you can take here. Right, obviously they are much easier to extract from Q values, because you're just doing max over the values that are already written there. Right, so what is wrong with value iteration? we touched on the complexity. Yeah, I think we covered this already last time. So the complexity in this case, let me write it down, is O A S squared, because I have to, I do this for every state. And then I do this for every action. And depending on how the environment is set up, in theory, I can from every state get to every other state, which doesn't have to be the case, but worst case or general case. And this gives me that. So it's basically S times A times S. Okay. And that's for one iteration. Remember, it's an iterative method, and we stop after we see that the values are not changing anymore, right? So this is still kind of times the number of iterations for the whole algorithm. And now we can make if you run this, you can make some observations. And one of them is that the policy doesn't change often. So you've seen it also in the live demos in the Berkeley lecture. Most of the time, the arrows, which were denoting the optimal policy in every state, most of the time they don't change. The values, they sort of change gradually, but yeah, only in very few moments the policy actually change. And so that means I'm considering all the actions over time and maximum over them. But it seems that this work, I'm doing a lot of work repeatedly, but the outcome is most of the time the same. So that's kind of the rationale, the observation for you to come from value iteration to policy iteration, to note that you're doing this work, but most of the time it's the same thing. It has the same outcome. The max action is almost always the same. And also the policy often converges long before the values. So that means the arrows, they just stop changing. And you can still iterate depending how you set the stopping criterion for the values. They get a little bit fine-tuned, but the policy will already not change anymore. And as we discussed, the policy is that's usually your priority, and so you might as well stop there. So that's the motivation for moving from value iteration to policy iteration. Right. Can we compute the policy directly? So that's what this is about. Before we do policy iteration, we need to do policy evaluation. So there are all these things. There is policy evaluation, there's policy extraction, there's value iteration, policy iteration. They are all connected. It's usually that you just do one ply of expecting max, but please try to think about what these four things mean. And I think this is also going to be important for you, for example, for the exam. So you will be asked, for example, to compute one or the other, and you have to sort of know what the differences between them are, that you really understand what does it mean, how you go from one to the other, and what the implications are. Okay, so now to do policy iteration, you need one step, which is policy evaluation. So you have a policy, which is not the optimal policy. You have a policy and you want to evaluate. So that means you're not maxing over all the actions. You just take the action that policy pi describes. So the max goes away. It's fixed. So there is no max operator, right? So there is this policy that tells you what to do. So that gives you the action, and that, of course, simplifies things. Right. So so there's pi of s. Okay. And so the value for that particular policy pi is the same thing. So there is it's basically like what we had for the Q values, right? But the Q values was take action A and then a policy thereafter. So here you just take that policy which prescribes the immediate action A and also all the actions that follow, but you don't compute that. We just do this one ply and then we plug in the values that we got from somewhere. That usually this iterative algorithm. Right. So yeah. So it's a V pi of S, pi being some policy. So how do you compute that? So this is the policy. Yeah. So this is it's the same thing what we did. Here, the important thing is that the policy is fixed. So I don't consider all the cases. I just consider this one, and then if these neighboring states have some values, then I just plug them in, and that's it. Okay. So that's nothing really new. And one thing that has sort of implications for how you compute it is that so the max operator is gone. And remember, we discussed value iteration and that the max operator is problematic. Do you remember what was the problem? Why was the max operator bothering us? So we had a system of equations that we wanted to solve. We had n equations with n unknowns, but somehow this was troubling the max operator there. What is the problem with the max over the actions? So I have this equation now for every state. It's a weighted sum of something. These are just the values from, let's say, the previous state, the previous iteration. I will have n such equations if I have n states, and I will have n unknowns, which are the new values. During value iteration, it was the same thing, but there was this taking the maximum over the rest, for the different actions you can take. This is not the case anymore. The action is now fixed because the action is this pi of S because I have a policy. And does it ring a bell? Okay, never mind. The problem with the max operator is because it's a nonlinear operator. So taking a maximum over something is not a linear operation. And then, in terms of solving a system of equations, that's a problem, right? And that's why basically the value iteration is an iterative algorithm that solves that. If the max operator is gone, which is this case, you have this system of linear equations. All the operations here are linear. It's multiplications and additions. So this gives you the opportunity to use a different way of solving it. Namely, you can just use linear algebra methods, for example, quadratic programming to solve this system of n equations with n unknowns. If the system is very small, you can even do it by hand. That's for this kind of scenario, it wouldn't be difficult. You just express one unknown in terms of the other. You plug it into another equation, and that's how you. I guess this is high school or even elementary school maths. So this gives you this additional opportunity of solving the system. If the system is really, really big, even such a linear system may be difficult to solve quickly. So you might do the iterative way anyhow, but it has become a simpler problem because the max operator is gone. So this is important to keep in mind. So how does this policy iteration work? You start with a random policy, you evaluate it, you improve it, and you repeat it until, importantly, policy converges, okay? Not until value converges, but until policy converges. This means, and with value, we had to have a certain threshold, value changes only by this much, and we can stop. Here, it's very simple. Basically, policy just prescribes which action to take. It's a discrete sort of world, which action to take in every state. And once, the arrows don't change anymore, you stop, and often this will be earlier than with the value iteration. Okay. Okay, question by Lukáš. I thought that we still use the max to get the optimal action. Yes, yeah, we will get to that. Yeah, use it here in the policy improvement, but you don't use it in the policy evaluation. So it's now split into two, and yeah, so you're still using it, but it has been, yeah, exactly. So it has been split up like that, and so now so this is what you're doing in every iteration of the policy iteration, and this is like the value iteration, which you have to do until convergence. So you may think, so how come I'm saving time because I'm still doing this, iterative thing, or I can also solve the system of equations. Right, but the fact that the max is gone is important. Well, first, because it has become linear, and second, because I don't have to, the time complexity, the A term disappears. So I'm actually saving a lot of time here by not going over all the actions. So that gives me sort of the boost in terms of time. And then I just do one ply of expectimax looking for the best action. So after I update the values, I use the values from the sort of old policy to check if I do this one ply of expectimax, trying the different actions and looking for the values of my neighbors. I see if I should change the policy. The ply I+1 is the new policy, and I just see if I should change the arrows now that I have the updated values. So that's the policy improvement. So that's basically the policy extraction from the values. So here, policy iteration means policy evaluation, and then basically policy extraction from the values that you got. And yeah, so so these are the two basic variants. In practice, there are also like something sort of in between, because you have to sort of imagine it depends on the particular actions are there, and also how connected the world is. If I can get from every state to the S in the complexity becomes very important. If I have a lot of actions I can take, the A becomes important, and this basically can, in practice, it also leads to some hybrid algorithms that consider that. The important thing is that both algorithms and also sort of somehow some things in between are optimal, provided that, as we discussed, there could be some heuristics. You sort of like to prioritize some states over others or some actions over others. Yes, every now and then, and in the long run, basically infinitely often that you visit all states and you update all actions, you will not lose the optimality, but you can get a speed up, in practical terms. Okay. So policy iteration algorithm. So you have this Markov decision process problem. Initial policy is random. Initial values are 0. And now you repeat. So this is the main loop. Now you do the policy evaluation, which is, this one value iteration, but without maxing over actions with that policy that you currently have, initially the random policy. This unchanged allows you to track whether there has been any change in the policy. And so after you do the policy evaluation for every state, you do this one ply of expectimax to see whether any of these arrows, so any of the actions for any state should change. And if any of them changes, you continue. But if none of them changes, you can stop. So basically, imagine you were lucky and you initially or after a few runs you basically had the arrows right. Then you just run the policy evaluation, and if the arrows don't change anymore, you can stop. And that as we have seen in some of the limos, often the arrow stop changes, let's say, quite early, after you get sort of propagated the important things, to that all states have the chance to reach the goal. Then after that, usually the arrows don't change so much, and after they really stop, you can stop even if the value is not the sort of final converged value. Okay, so you run until unchanged. So just a recap. Value iteration updates values, policy implicitly, so it primarily updates values and no track of the policy. Policy iteration update of the values is faster because you're not maxing over actions. New policy from values, and new policy is better or done. Yeah, this is slower because you have to do that max, but this is this one ply of expecting max. Dynamic programming rearm. Okay, let me just see. The complexity, the policy. We discussed, I think, the complexity, and I think this is fine for our purposes. The policy, just that you know that the policy evaluation complexity. So policy evaluation is here. Policy evaluation is OS to the power of 3, right? There is no A, but there is the number of states to the power of 3, and that can also be used using linear algebra methods. For small state spaces, it's okay. Right, and so references, as I also said last time, we're sort of moving from this book to this book, and in particular, so this book focuses on reinforcement learning, and this is also what we will be starting next time, which is after the Easter break. In the Berkeley lecture at the end, you had this this Bandit introduction. So one-armed Bandit, it just means it's this slot machine that has this one arm, and so the idea here is that up until now we had a non-deterministic agent, but we had a sort of map of the environment. We had the transition probabilities. We knew everything. We just couldn't count on the outcome of action for sure, but that was where the uncertainty was. And what we will do next is we will have no such map or no such, we will not have the environment will not be observable in this sense. We will not have ahead of time this kind of overview. Instead, we will just keep trying. So one thing is with this, we have two slot machines. You pull this lever, you get coins or not. You pull this lever, you get coins or not, and you just record these episodes, and you try to figure out which slot machine is the one you should pick. And this is what is called reinforcement learning, that you will get the reward as you go, and you try to build a policy or a model of the environment, depending on how you approach it, or both as you go. So it's basically like the problem we had. You would be starting in the start position, but you will not see where this thing is going. You will just try up or right. You will get some reward or penalty, and you will try right again, and you will be recording those episodes, and the point is to find the optimal action or the optimal policy just from experience, without somebody giving you those transition probabilities ahead of time. So that will be reinforcement learning. So coming back also for those of you who joined later. Questions for this lecture before I leave the slide? Doesn't seem so. Okay. Right. So we finished here. Here are the slides that you have seen today. Right now, after the lecture, I will update, as usual, the slides with notes where you have extra information and also solutions to the quizzes and everything. Just again, for Rufat in particular, next week there is no lecture and also no lab. There is Easter Monday, and we will reconvene in 2 weeks with reinforcement learning. It's very likely that we will continue, in this way, in this online form, also in 2 weeks. So we just count on that. Otherwise, I think you can assume you will get a notification. And we do this reinforcement learning 1. So please watch this lecture before our lecture, and and then again we use the same mode like up until now. Then we have 2 lectures on reinforcement learning, and then there will be this midterm exam where you can basically expect things like this kind of interactive. It's very similar to the quizzes, also what you do in the labs, that you will be mostly given problems to solve. So problems that you can solve on paper, so nothing really complicated. But you might be asked to do a couple of iterations of one algorithm or the other, and these kind of things, or do alpha beta pruning of a simple tree. So just that you know what to expect. It's not going to be theory. It's going to be more applied application of the knowledge from the lectures and the labs. Okay, any questions? No questions? Okay, so you will see Philip at the lab in the afternoon, and we will see each other in 2 weeks. So I wish you a nice Easter break, and take care.
Thank you. Bye-bye.
Bye-bye.